Tuna are not just another fish on our plates. They are among the ocean's most extraordinary athletes. Built like streamlined torpedoes, wired with physiology that pushes the limits of what fish can do, and capable of crossing entire oceans, tunas are biological marvels. But their story is not only biological, it is also deeply historical, stretching back thousands of years. From the harpoons of ancient hunters to the billion-dollar global fisheries of today, tuna have been at the center of a relationship between humans and the sea that continues to shape both. Tunas belong to a group of fishes called the Thunini, a tribe within the mackerel family. This group contains multiple species, including the famous bluefins, yellowfin, albacore, big-eye, and skipjack. They range across all the world's oceans, from warm tropical waters to colder temperate seas. Though diverse, all tuna share a striking set of adaptations: streamlined bodies, crescent tails, and physiology tuned for speed and endurance. The body of a tuna is a product of evolutionary refinement. Unlike most fishes that undulate their bodies, tunas keep themselves rigid and drive propulsion almost entirely with their crescent-shaped tails. This method, called thunniform locomotion, produces powerful lift-based thrust. Small finlets along their backs and bellies, once thought decorative, actually reduce turbulence and drag, boosting efficiency. Every detail of their anatomy is shaped by the demands of life in the open ocean, where speed and stamina mean survival. Popular accounts often claim tunas can sprint at 70 or even 80 kilometers per hour. Modern science paints a subtler picture. Yellowfin tuna, for example, are capable of bursts around 48 kilometers per hour, with cruising speeds that can be maintained for hours. Their true superpower is not raw top speed, but the balance of strength and endurance over vast distances, making them the marathon runners of the sea. Unlike most fish, tuna are partially warm-blooded, a condition called regional endothermy. Heat generated by deep red muscles near the spine is recycled using networks of countercurrent blood vessels known as retia mirabilia. These keep muscles, the brain, and even the eyes warmer than the surrounding water. This adaptation boosts muscle performance in colder waters and sharpens neural processing, giving tunas an edge as relentless predators. By warming the eyes and brain, tuna gain enhanced sensory abilities. In cold seas, most fish experience slower nerve conduction and reduced vision. Tunas, however, keep their retinas and brains running hot. This sharpens their eyesight, allowing them to detect fast flickering movements even in dim light, and helps them coordinate high-speed chases with remarkable accuracy. To power such demanding performance, tuna must process oxygen at extraordinary rates. They are obligate ram ventilators, which means they must swim constantly to breathe, pushing water over their gills. Their gill surface area is among the largest for any fish, supporting immense oxygen uptake. Their hearts are built for endurance, pumping with high volume and force. Even their blood chemistry is tuned for extremes. Big-eye tuna, for instance, maintain oxygen transport even in the cold, oxygen-poor waters of the deep ocean. Electronic tagging has revealed the epic journeys of tuna. Atlantic bluefin tuna routinely cross the entire ocean, traveling from the Americas to Europe and back within a year. They also dive to astonishing depths, sometimes beyond 1,000 meters, into cold, dark, oxygen-poor waters. Big-eye tuna are specialists in this realm, spending long hours in deep, low-oxygen layers during the day, then returning to the surface to warm their bodies before diving again. Unlike many fishes, tunas have reduced or absent swim bladders. This frees them from the constraints of pressure changes, allowing rapid vertical movement without injury. Instead, they maintain position using continuous swimming and hydrodynamic lift from their fins. The price is constant motion. For a tuna, stillness means suffocation. Tunas are prolific spawners. Females release millions of tiny eggs into warm waters, with species like yellowfin spawning almost daily during peak seasons. Atlantic bluefin spawn in specific regions such as the Gulf of Mexico and the Mediterranean Sea, timed to narrow seasonal windows. Despite their relentless lifestyle, tunas can live surprisingly long lives. Yellowfin for about a decade, while bluefin may reach 40 years, growing to more than 3 meters in length and weighing over 600 kilograms. Human fascination with tuna stretches back millennia. Ancient Mediterranean cultures, from the Phoenicians to the Greeks and Romans, hunted bluefin tuna in great seasonal runs. Archaeological evidence shows large-scale tuna fishing in Spain, Sicily, and North Africa as early as 2,000 years ago. In Roman times, tuna was a prized commodity, preserved in salt and traded across the empire. Traditional trap fisheries, known as almadrabas in Spain and tonara in Italy, have been used for centuries and still operate in some places today. In Japan, tuna fishing and consumption also have deep roots, but it was in the 20th century that bluefin tuna became a global delicacy. With the rise of refrigeration, freezing technology, and the international sushi trade, demand for fatty bluefin soared. By the late 20th century, massive industrial fleets targeted tuna across the world, driving populations into steep decline. A single giant bluefin could sell for hundreds of thousands, and in some cases, millions, of dollars at auction, turning this once local fishery into a high-stakes global market. Intense fishing pressure left many tuna stocks severely depleted. Atlantic bluefin in particular fell to alarmingly low levels. In recent decades, international agreements, quotas, and stricter enforcement have helped some populations stabilize and even recover. In 2021, the Atlantic bluefin's global conservation status improved, though regional populations remain fragile. Other species, such as the southern bluefin, remain endangered, and the future of tuna will depend on careful management, science-based quotas, and sustainable practices. For humans, tuna is both a valuable source of nutrition and a risk to manage. It is high in protein and rich in omega-3 fatty acids, but large species accumulate mercury over their long lives. Smaller species like skipjack are generally safer for regular consumption, while larger species like big eye and bluefin carry higher mercury levels, making them less advisable for children and pregnant women. The story of tuna is one of biology and history intertwined. They are ocean-crossing predators whose bodies are built for speed, endurance, and survival in extreme environments. They are also a part of human history, from the fishing traps of antiquity to the global markets of today. As we continue to study, fish, and consume them, we must balance our admiration and appetite with the responsibility to protect them. The next time you think of tuna, remember that you are looking at one of nature's most finely engineered creatures, and one of humanity's oldest companions from the sea.